Okay, so this was where we stopped the last time. Let me just go over what we did. So we're looking at the Simpson's 1/3 rule. So we derived the formula for just one single segment. For a single segment, the formula we derived is given by this formula. We did an example. Then we also derived the formula for the multiple segments using Simpson's 1/3 rule. So to reiterate, Simpson's 1/3 rule is used to find the integral of a function, but the function is approximated with a second order polynomial. For trapezoid rule, the function is, we approximate the function with a first order polynomial, which wasn't so accurate. But when we increased the order of the polynomial to 2, then we had a more accurate result. Then I said that it's used when n is the number of segments. When n is even, that's when Simpson's 1/3 rule can be applied for. And why is it the case? It's because you are using a second order polynomial. So you are using a 2-order polynomial, and 2-order polynomial is even. So the number of segments that you want to divide the function into must be even in order to use Simpson's 1/3 rule. So you need 3 points, and the number of segments should be even. So for 3 points, you have 2 segments. For 3 points, you have 2 segments. Then we started this example. We want to use Simpson's 1/3 rule to estimate the value of this integral when n is 4. So n must be even for you to use Simpson's 1/3 rule. And we calculated the step size, or the interval, as you will call it. We calculated the step size as 0.2 using your upper limit, your lower limit, and the number of segments as 0.2. Having calculated the step size, we need to, since we're using, this is Simpson's 1/3 rule, and n is equal to 4. So definitely, we need to calculate f of x naught. This is f of x naught to f of xn, because where n is equal to 4 in this case. So this is f of x, this is x naught to xn, but in steps of 0.2, because our step size or our interval is 0.2. So we start from 0.2. We start from 0. 0 plus 0.2 is 0.2. 0.2 plus 0.2 is 0.4. 0.4 plus 0.2 is 0.6. 0.6 plus 0.2 is 0.8. So that's how you calculate, that's how you get the value of the function you need. So from x naught to xn. And this is the formula for Simpson's 1/3 rule. So this is your x naught, which is the lower limit. This is the value of the function at xn, which is your upper limit. Then in between, you have this interval. So this is in between your upper limit and your lower limit. So when I is odd, you multiply it by a factor of 4. When I is even, you multiply it by a factor of 2. So we have these values. So definitely, these are our x naught, x1, x2, x3 and x4. So putting this in terms of the number of segments we have, since n is 4, we are going from x0 to x4. And in between these values, when you have even, when your I is even, you scale it with 4. When I is odd, so you scale it with 2. So the next one should have been plus f of x4, but the last value is x4. So you cannot scale it with 2 here, because the last value is on its own and the first value is on its own. So when you arrive at this formula and just put in the value of the function which you've calculated previously, we would arrive, and putting on the values, we arrive at a value of 1.62. We are told that the true value of the integral, which is like the analytical solution, is 1.64. And when we track the error, we got an error of 1%. So this is, like I said previously, the error is a lot lower compared to the previous case where we had 16%. So in this case, we had 16%, and we're using Simpson's 1/3 rule, but we used just one single segment. It was just one single segment, but when we increased the number of segments, the error reduced drastically. So we go to the next Newton-Cotes formula for numerical integration, which is Simpson's 3/8 rule. As you would have guessed, for Simpson's 1/3 rule, we are using a second order polynomial in place of the function you want to integrate. So in place of this f of x, we are using a second order polynomial for Simpson's 1/3 rule. But for Simpson's 3/8 rule, we're using a third order polynomial to approximate the function given by f of 3x. So 3 being a third, the 3 here represents a third order polynomial. And I actually skip the steps. So is similarly to the last step. In the last class, we said that we use the second order Lagrange polynomial, which we derived in the last lesson. But for this one, you use the third order Lagrange polynomial, which we derived also in the last class. And when you do all that, you arrive at this formula. So this is a formula for Simpson's 3/8 rule. 3/8. The reason why we use where this 3/8 comes from is from this 3/8, because at the end of the day, when you derive the formula, h, which is the interval or the step size, is scaled by a factor of 3/8. Then h, for single segments, h, the step size, is given by b minus a divided by 3. Remember, for the Simpson's 1/3 rule, for the single segments, h was given by b minus a divided by 2, being a second order polynomial. That's why you have this 2. For a single segment, you have this 2. But for Simpson's 3/8 rule, you have a third order polynomial for a single segment. So this is where the 3 comes from. So the step size is given by this equation. And in place of this h, if you replace it by this equation, so this is an alternative equation for the Simpson's 3/8 rule. So the 3/8 came from here. And I said that the Simpson's 1/3 rule is you can only use it when the number of segments you want to divide into is even. And as you would have guessed, for the Simpson's 3/8 rule, you can only use it when the number of segments you want to divide the function into, that's for multiple application. For multiple application, Simpson's, for multiple segments, Simpson's 3/8 rule, you can only use it when the number of segments you want to divide the function into is odd. That is when you can use the 3/8 rule. So in general, the 1/8 rule of Simpson's method of integration, it's much accurate and is sufficient. In fact, there would have not been any need to actually come up with another Simpson's rule, which is 3/8. It's very accurate in that it's very close. The integral we're going to get is very close to the analytical solution. But the only disadvantage of the 1/3 rule is that you can only divide the number of segments in even. That's when the number of segments is even. That's the only disadvantage of that rule. So in general, we use the Simpson's 1/3 rule. But once the number of segments is odd, we combine. We don't actually use the 3/8 rule on its own. We, as much as possible, we try to use the 1/3 rule. That's when the number of segments is even. We try as much as possible to use the 1/3 rule. But when the number of segments is odd, we try to combine it in a way that we can use the 1/3 rule and the 3/8 rule. For instance, in this case, the number of segments, you have 1, 2, 3, 4, 5. You have 5 segments, n is equal to 5. And that n is equal to 5 is odd. So definitely, we cannot use the 1/3 rule because it's odd. But instead of us using the 3/8 rule, just like that, we combine it with the 1/3 rule because the 1/3 rule is actually much more accurate than the 3/3 rule. So in this particular example, n is equal to 5. So we know that we cannot use the 1/3 rule. So we combine it in such a way that we divide it into 2. So we said that we divide it into 2 parts for n is equal to 2 and for n is equal to 3. So 2 plus 3 will give us the 5. So within 2, for the first 2 segments, we used the 1/3 rule. Then for the remaining 3 segments, we use the 3/8 rule. That's the way we do it because the 1/3 rule is more preferred than the 3/8 rule, as we will be seeing. You might be tempted to think that why can't we divide it into n is equal to 4 and after that n is equal to 1. So 4 plus 1 will give us 5. So we can use the Simpson's 1/3 rule for the first 4 segments. But then if you use the 1/3 rule for the first 4 segments, the last segment, you cannot use Simpson's 3/8 rule because you need at least 3 points in order to use the 3/8 rule. And now you just have 2 points left. So for 2 points is the trapezoid rule you can use. And we know that the trapezoid rule is not very accurate. It has a large error. So we divide it in such a way that we use Simpson's 1/2 rule for the first 2 segments. Then the last 3 segments, we use the 3/8 rule. So let's do an example. want to use the Simpson's 3/8 rule to integrate this function. And the 3/8 rule is a third order polynomial. And for a third order polynomial, you need 4 points. You need 4 points in order to approximate the function as a third order polynomial. So we discussed it last class about that. So we need 4 points. So for 1/8 rule, you're approximating with a third order polynomial. So your step size or your interval is 3 because you have a third order polynomial. So a third order polynomial will give you 4 points. So when you calculate this, you arrive at 0.2667. 0.2667 is your step size. So is your interval. So definitely with this now, the lower limit is 0. That's x of 0. The next one is your step size. That's 0.667. So that's the next one. Okay, there's a question. Why do internal segments divided and first and last not divided from the figure you explained? Okay, so why are the internal segments divided and the first and last are not divided from the figure you explained? Okay, from this figure, this is the limit of integration from 0 to 0.8. So this is the limit. This is the lower limit and this is the upper limit. So we want to divide, the number of segments we have here is 5. And we want to divide it into, it's already divided into 5. So that means that these are the steps you will take from 0.2, 0.4, and 0.6. So what I'm saying is that, what I'm explaining from this figure is that you can only use the 1/3 rule when the number of segments is even. So 1, 2, this is even, you can use 1/3 rule. But when it's odd, you can only use the 3/8 rule. And the least number of points you should have is 4 points. So you have 1, 2, 3, 4. So the reason why we divided this into, we divided the inner segment is that we cannot just want to use multiple segments in order to find the integral of this function. Want to use multiple segments. And so we divided it into 5. But the best approach would have been to use Simpson's 3/8 rule because n is odd for everything. But what I'm saying is that the 3/8 rule is not so very accurate. It's the 1/3 rule that is much more accurate than this. So the line of action means that since the 1/3 rule is more preferred than the 3/8 rule, we have 5 segments. So we divide it into 2. So when for 2 and 3, 2 plus 3 will give us 5. So we use 1/3 rule for the first 2. Then for the last 3, we use 1/8 rule. That's why we divided it in that way. So it's just the internal segments you are dividing. So in this question, we want to use Simpson's 3/8 rule to find the integral of this function. And is a third order polynomial. It's a third order polynomial. So you need 4 points for that. But first of all, you need to get the step size. And since it's just a single segment and it's a third order, so you are dividing by 3. So your step size is 0.667. From that, we need to get the value of the function at the lower limit, then at the upper limit. So the lower limit is 0 and the upper limit is 0.8. Then the step size is, so in between 0 and 0.8, you have some value of the function given by the step size. So the first step size is just 0.2667. So you evaluate the function at this particular step size. Then the next step size is 0.2667 plus 0.2667. So that's the next step size. Okay, there's a question. Why is it third order? I can see the highest degree being 5. Okay, so thank you for that question. Okay, you are saying that why are we using a third order when the highest degree is being 5? Okay, the reason is that when I started this class, I'm not sure if you joined in when I started this class. When I started this class, I said that we have, let me just go over it. So this is the method you use to differentiate, and this is the method you use to integrate analytically. So you all know how to integrate and differentiate. But in this class, we are looking at numerical solution to integration. That's what this class is all about. Numerical approach to integrating. And we have different methods. Like I said previously, you have the trapezoidal rule, we have the Simpson's 1/3 rule, and we have the Simpson's 3/8, 1/3 rule and 3/8 rule. So this is the function you are giving in the question. It can be any order of polynomial, but for trapezoidal rule, you are approximating the function with a first order polynomial. That's for trapezoidal rule. You are approximating this function you want to integrate. It can be a fifth order polynomial. It can be a seventh order polynomial. It can be a 50th order polynomial. But for the trapezoidal rule, you are approximating this function with a first order polynomial. That's for trapezoidal rule. For Simpson's 1/3 rule, you are approximating the polynomial that you want to integrate with a second order polynomial. That's for Simpson's 1/3 rule. You are approximating this polynomial that you want to integrate with a second order polynomial. We don't care about the order of the polynomial. We are not interested with the order of the polynomial. All our interest is that we want to integrate this function, and we don't want to make use of the analytical solution, which is the method you would have considered previously in your undergraduate and in your further maths class. We don't want to make use of the analytical solution. We want to make use of the numerical solution, which is an approximate solution. And the reason why we want to approximate is that if the function is very, very simple, you can just easily use the analytical methods and integrate, and there's not going to be any problem whatsoever. But if this function is very, very complex, if it's very, very complicated, using the analytical solution there may not even be any analytical solution to find the integral of this function. So for Simpson's 1/3 rule, you are approximating this function with a second order polynomial. Then for the 3/8 rule, for the Simpson's 3/8 rule, you are approximating the function that you want to integrate with a third order polynomial. You're just approximating it, because now we are making use of numerical methods to integration. So in this particular question, this is a fifth order polynomial we want to integrate, quite all right. But we want to make use of Simpson's 3/8 rule. So we are going to approximate it with a third order polynomial. So that's where this 3 comes from, because you are approximating with a third order polynomial. So this is the how to get your step size. So b minus a divided by 3. So since you are using a 3 order polynomial, that's where the 3 comes from. When we're using 1/3 rule, that is a second order polynomial. So we did b minus a divided by 2 for a single segment 1/3 rule, because it's a second order polynomial. That's where this 2 comes from, and a single segment. So you have this 2 here. If it was multiple segment, then it's n in place of 2. For the 3/8 rule, that is where the 3 is coming from, because you have a third order polynomial. We're using a third order polynomial to approximate this function. And here, n is equal to 3. So you have 3 here. So when you use this formula and you get the step size, you use this formula to get your step size. And your step size is, from this you got 0.667. That's the step size. That's the step size. Then we're going to evaluate the function at the lower limit. Then we evaluate the function at the upper limit. So these are our lower limits and these are our upper limits. So in between the lower limit and the upper limits, you have some points in between the lower limit and the upper limit. Okay, another question. What if the degree is much higher? Won't there be any error in the model solution? Okay, the answer to your question is that, I don't know if you started this class with us, but when we used first order polynomial to approximate the function and we did the integration, this was the value of the results we got, but this is the exact solution of the integration. So if you observe, the error is very large, like you've rightly pointed out. But the way we reduced the error is that we made use of multiple segments. So instead of just integrating from the upper limit to the lower limit, we divided the number of segments into integer values. Then we approximated the function using a first order polynomial within that interval. So when we did that, our error reduced. So it's reduced to 39%. Then we used a computer program, because we know that as we increase the number of segments, the error is reducing and we are getting closer to the analytical solution. So instead of doing the calculation by hand, because as the number of segments increases, the calculation too is going to increase. So we wrote a computer program that will actually do multiple segments for us. And the result of that computer program, it gave us these values. So when we had 100 segments, the error was very, very little, because the numerical integration is 1.64. So we actually got closer to the analytical solution, even just approximating the function, which is a fifth order polynomial, even just approximating the function with the first order polynomial, but using multiple segments, 100 segments, we got close, very, very close to the solution. So we've already discussed all that. So it gives error, but in order to reduce the error, just use multiple number of segments. So back to this example I was saying. So for third order polynomial, for third order approximation is the Simpson's 3/h rule, and the step size is given by this formula, which is this. So this is your lower limit. So the next step size is 0.0267, which is this. The next step size is 0.2667 plus 0.2667, which will give you this. The next step size is this plus 0.2667, which will give you this. So you are using a third order polynomial and you need 4 points. This is your first point, your second point, your third point, and your fourth point. So this is f of x1, f of x2, f of x3, then f of x4. And this f of x4. So you have 4 points now, because for a third order polynomial, you need 4 points. So using this approach, we derived the formula for Simpson's 3/h rule as this. So we already have the f of x0, f of x1, f of x2, and f of x3. So given by this equation. So let me go back. So this was the equation we derived. So we already got it f of x0, f of x1, f of x2, and f of x3 based on the value of the function given to us in the question. So it is this function you will use to approximate for f of x0. It is this function that you use to approximate for f of x 0.2667. So this function, so in place of x, you put this. So once we already got all we need. We know b, we know a, then we know all the values we want to know. Then just simply plugging in the values, we got this. So this is the exact numerical, so this is the exact solution, the analytical solution, and this is the numerical solution. So when we track the error is 7.4%. And if you look at it carefully, you are using, this is the third order polynomial we're using. I told you previously that the Simpson 1/3 rule is actually much preferred, is better than the 3/h rule, even though the 1/3 rule is the second order polynomial, while the 3/h rule is a third order polynomial. We got an error of 7.4% when doing the numerical integration. But when we use the 1/3 rule, the error we got was for multiple segments, the error we got was 1%. So this goes to show you that though for single segments, it was for single segments, the error we got was like 16%. The error we got was 16%. But when we use multiple segments, we got 1%. Then for Simpson's 3/h rule, we got 7.8%. So the result of this is telling you that, like what I said previously here, that the Simpsons 1/3 rule is actually a better method. Is the best method that we should normally use. But the only disadvantage is that it can only be used when n is even, when the number of segments you want to divide into is even. That's the only limitation. So definitely when the number of segments is odd, you just use the 3/8 rule. So, but in this case, the number of segments we have is 1, 2, 3, 4, 5. We have odd number of segments. So you might be thinking that, okay, let's just use the 3/8 rule. But the 1/8 rule the 1/3 rule achieves a better accuracy. So what we do in this case is that we divide it into, you have 5 segments, which is odd. So we divide it into 2 and 3. So 2 plus 3 will give you 5. So for the first 2 segments, for year and year, you use the 1/3 rule. Then for the remaining segment, which is odd, you use the 3/8 rule. That's the way we do it. You might say that, why can't we use, because there are 5 segments, right? So you might say that, why can't we use, for the first 4 segments, that's 1, 2, 3, 4, let's use the 1/3 rule. But if we do it this way, you just have 1 segment remaining. And for 3/8 rule, you need at least 3 points. You need at least, 4 points for the 3/8 rule. So you just have 2 points. So you cannot use the 3/8 rule. You can only use the trapezoid rule, because for the trapezoid rule is a first order polynomial, so you need 2 points. And the trapezoid rule, like we saw, is not very accurate. So it's better to break it down into 2. We use 1/3 rule for the first 2. Then the last 3, we use the 3/8 rule. So that's the way we do it. So in the part B part, we are asked to use Simpson's 1/3 rule to integrate the same function for 5 segments. So first of all, we use the 3/8 rule, first of all, which we just did. And now we are asked to use the 1/3 rule for 5 segments. So as you would have observed with this question, the 1/3 rule can only be used when the number of segments is even. But now we are asked to use it to find the integration for 5 segments. So how are we going to do that? I've already explained how to do that. The way you do that is that you use for the first 2 segments, we're going to use the 1/3 rule. Then for the last 3 segments, we use the 3/8 rule. So that's what we are going to do. So in this question, n is equal to 5. So we get the step size h as 0.16 using this formula. Then this is our f of x naught, and this is our f of xn. So we need to get the values in between using this step size of 0.16. So after the lower limit, the next value is 0 plus 0.16, which is 0.16. After this, the next one is 0.16 plus 0.16, which is 0.32, because our step size is 0.16. After this, you add 0.16 to this to give you the next value of the function which you are going to evaluate. After this, you are going to add this with the step size, which is 0.16, to give you the next interval, sub-interval you will evaluate the function with. Then finally, you add this value to 0.16. Then you get the last upper limit at which you will evaluate the function with. So we have 5 segments we divided into the function into, and this is the lower limit, this is your upper limit. So you need to get the values in between which is given by this step size. So the interval between this and this is 0.16. The interval between this and this is 0.16. The interval between this and this is 0.16. And the interval between this and this is 0.16. So we have like equal number of intervals. So the intervals are equal. So when we evaluate the function is given to us in the question. At f of 0, the function is 0.2. At f of 0.16, this is the value of the function. So at this value of x, you have this value of the function. So what we've done is that we've successfully divided the function into 5 segments. Now, we are asked to use the 1/3 rule, but we can only use the 1/3 rule when the number of segments is even. So for the first 2 segments, like I said, we use the 1/3 rule. Then for the last 3 segments, we use the 3/8 rule. So going by that, this is the formula for the 1/3 rule. So this is our f of x naught. So we need f of x naught, f of x1, f of x2. That's what we need. Then for the remaining last 3 segments, you will start from f of x2. You start from f of x2, then you end at the last limit. That's f of x5. So this is f of x2, f of x3, f of x4, f of x5. So for the 3/8 rule, you need 4 points. Then for the 1/3 rule, you need 3 points. So these are the 3 points you need for the 1/3 rule, and these are the 4 points you need for the 3/8 rule. And obviously they have different formulas which we derived. So putting in the values, so f of x naught is f of 0, f of x1 is 0.16, then f of x2 is 0.32. So putting in all these values, so we've already evaluated the function here. So this is what we got. So for the last 3 segments, you started from x naught and you ended with x2 because we need 3 points. So for the last 3 segments, you start from x2 and you end at the last point using the formula for 3/8 rule. So we already know the value of this function, and which is given by 0.32, 0.48, 0.64, and 0.8. So we already know that. So we simply put in the values, then we arrive at this. So the integral, the total integral, we divided it. We have 5 segments. So for the first 2, we use 1/3 rule and we got this. For the last 3 segments, we used 3/8 rule and we got this. So the integral of the function is just given by the addition of this and this. And when we did the addition, we got 1.64. The true value of the integration is this. And when we track the error, we had 0.3%. Is actually an absolute value. So this minus can go because it's just the absolute error. So the result of this example is telling us that when we used 2 methods, when we incorporated 2 methods to solving the integral using numerical integration, we had a much less error. So the summary is that it's good to incorporate, the summary of this is that it's good to incorporate 2 methods. So the first one is that for this particular example, we first of all use just single segment 3/8 rule to integrate, to do the numerical integration. And we got 7.4%. But when we combined two methods together, so we combined the 1/3 rule and the 3/8 rule, we had an error of 0.3%, which is very, very low. So in conclusion, I'm just repeating what I said here. In conclusion, the 1/3 rule is very good. The most preferred method is the 1/3 rule. But the only limitation is that you can only use it when the number of segments is odd. So given that case, you already know that your most preferred method is the 1/3 rule. So given an odd number of segments, you will divide it into two such that you will still be able to use the 1/3 rule for one portion of the function. Then for the remaining portion of the function, which is odd, you can use the 1/3 rule. Like I said previously, you might say that why can't we divide it into this, that since 4 is even, we should use 1/3 rule. But if we do it this way, for the first 4, 1, 2, 3, 4, we use the 1/3 rule. Then this part is remaining. And for this part, we have 2 points. But for the 3/8 rule, we need at least 4 points. In order to use the 3/8 rule, we need at least 4 points. And you just have 1 point left. And that means that you can only use the trapezoid rule. So it's counterproductive. We are using a very, very good approximation here, but you're using a very, very bad approximation here. But so the result is going to give you a very poor result. But the most preferred method is that you're going to use the 1/3 rule, then the 3/8 rule, and the result, like we've just done, will give you a much more accurate numerical approximation of the integral. So we are going to go into the Vba code because now we all know how to do this using hand calculation, using manual calculation, but we want to be able to use the computer to help us to do it, especially if the number of segments is large. We cannot be doing the manual calculation because it's very complicated. So this is the code for the 1/3 rule. So the 1/3 rule for single segments. The 1/3 rule for single segment is given by this. So this is the 1/3 rule for single segment. Let me bring it down here. So this expression is simply this expression, but now in code format. So this is b minus a, this is b minus a. This is f of x naught. So this is the lower limit. F of x2 is the upper limit, which is f of b. Then this value is the midpoint between the upper and the lower limit. And the midpoint is simply a plus b divided by 2. That's how we got this. Then for the 3/8 rule, single segments, the formula is given up here. So let me just copy it. This is the formula here. So to transfer it in equation form, in code format, we'll make use of this. So to transfer it in code format, you make use of this. So this is your b minus a here. So this is f of x at the lower limit. This is f of x at the upper limit. Then you need, for 1/3 rule, single segment, your step size is b minus a divided by 3. So you need this step size. So this is the lower position. Then the upper position is simply the step size you calculated here, which is f of h. Then the midpoint, because you need 4 points. you need at least 4 points for the 3/8 rule. So the next of points you need to calculate is it's somewhere in between this step size and this step size, and it's just given by b minus h. So yeah, since this is the last limit, so the previous interval is just going to be b minus h, because if you look at this, if you look at the way we calculated the step sizes, after calculating h, which is our step size, it's just, this is your lower limit, this is your upper limit. So the value here, just before the upper limit, is 0.8 minus h, 0.8 minus 0.16, which is 0.64. So it's that same method I used to get this value. So this upper limit minus the step size is this particular f of x2. And all of them, all these values are weighted by 3. So that's where this 3 came from. Then all of these is divided by 8. That's where this 8 came from. Then for Simpson's 1/3 rule, multiple segments, because if we want more accuracy, we need to increase the number of segments. So let me bring out the formula from which I derived the equation for. So this is the formula for this is the formula for Simpson's 1/3 rule. So let me bring it down here so that I can use it to explain the code. So here is the formula here. So for the multiple segment, this is the formula. So we need to calculate for h. Actually, let me use the formula with the h step size. Okay, so let me use this formula instead. So this is the formula I'm using. You can also use this formula. They are the same thing. It's just that b minus a divided by n is h. So that's just the difference. They are both the same thing. So first of all, you need to calculate your h. And your h is simply b minus a divided by n. Then you need to evaluate the function at the lower limit, which is f of a. Then there's this summation. So that's why we have this variable to help us to keep summing it. Then we need to evaluate the function at the upper limit, which is f of b. So now the next thing we need to do is to evaluate this function. So here, when I is odd, you multiply by 4. Then when I is even, you multiply by 2. So this is how we do it. So we start from 1. So 1 is odd. So definitely you multiply by 4 with this step size. So this is your step size. Then this is the first one. Then when you add 2 to an odd number, to give you an odd number. So that's why we added 2, such that for this summation, we are going to simply multiply 4 by this, just for odd numbers. Then for even numbers, we started with 2. So that's where this 2 came in. Then you multiply by 2 times the step size. So that's this. Then an even number added with an even number will give you an even number. So that's why we kept on incrementing by 2. such that for even numbers of I, you are going to multiply, you do this multiplication by 2. But for odd numbers, you will do this multiplication by 4. Then for I greater or equal to n, so you are not going to, that's where this n minus, that is where this m minus 1 comes in. Then for I greater or equal to n, so that's where this also comes in, such that you will not get to n, so that the last value at the lower limit will be on its own. You don't need to multiply it by any constant. Then after getting all this summation, the result, you're going to multiply it by h divided by 3. So that's where this h divided by 3 came into. So let me go to Excel. So this is um, Excel VBA. So this is Excel VBA. So this is a code we've written for the Simpson's 1/3 rule. Then this is the code for the 1/3 rule, single segment, single segment. Then for the multiple segments, this is the code that I've just explained. So in order to call it, since the function is of this format, I'll just copy it. Then I'll go to the Excel worksheet. So to call it, I'll just say that is equal to this b comma a. So in this sheet, I've defined b as 0.8 and a as 0. So that's simply, so once I do this, so this was what we got in the, when we did it by hand. Then for the, to use the 3/8 rule, you just copy the function, then in, so I already know b and a in the previous sheet. So this was what we got when we did it by hand. Then in order to do for multiple segments, 1/3 rule, you just call it this way. So I copy it. So when I go to the Excel worksheet, I'll just say is equal to this. So I already know AB, but I told you that n should be an even number. So let me put 2. So this is the result. Then when n is 4, I think we did 4 in the notes. So this was what we got when n is 4. So similar to what we did, you can just use the rule. So let me put n here. Then this will be the integral. Then you have 2, 4, 6, 8, and 10. So let me call it equal to, so in place of n, I will put m2, because cell L2 has our value of n. So for the